All right, so you might be wondering, if things are radioactive on this Earth, constantly spontaneously decaying, how do we actually still have radioactive isotopes if our Earth is billions and millions of years old? Well, actually, it takes a long time for things to decay. It doesn't happen instantly. Sometimes it does, but sometimes it happens over millions of years, such as uranium. The half-life of uranium takes millions of years, meaning that when the Earth started, we had a certain amount, and now we have, after 4.5, I think, billion years or million years, half of the amount of uranium is actually left on this Earth. So what do I mean by half-life? So half-life is the time required for half of the radioisotope's nuclei to decay. So let's take strontium-90, for example. It's a radioactive isotope. Its half-life is 29 years. So if I have no time passed by and no years, so no half-lives, I have in my possession 10 grams of strontium-90. Okay, so one half-life flows by, and that's 29 years. So 29 years later, my 10 grams that I originally had, half of it is left, as the definition of half-life states. So that means I have 5 grams of strontium-90 left. Okay. After 2 half-lives go by, 58 years, my original sample of 10 grams has gone through 2 half-lives. Half of it's gone after the first 29 years, and again, another half after the second 29 years, giving me 2.5 grams left after 58 years, and so on and so forth, until actually no atoms are left of strontium-90. So we could do this and fill out the chart and do this step by step by step by step, and it'll take a long time. Or we can go and translate this into a formula. And the formula basically says the amount remaining, how much we have, is equal to the initial amount, which is what we did, 10, times 1/2, which is exactly what we did, times to the nth power. So the n is the number of half-lives we went through. So for the first half-life, I had 1. Second half-life, we had 1/2 times 2, which is squared. Or not 1/2 times 1/2, which is squared. So the number of half-lives is n. Okay, so we can actually break down that n too, because we might want to know like fractional half-lives or things that are not full half-lives. So let's break that down even further and say the number of half-lives, which is we're going to denote as n, equals little t, which is the time that went by, divided by big T, which is the length of the half-life. Okay, so let's actually put this and do this problem together. All right, so let's say we have iron-59. A radioactive isotope of iron is used in medicine to diagnose blood circulation disorders. Okay, the half-life of iron-59 is 44.5 days. How much of a 2-gram sample will remain after 133.5 days? Okay, so let's actually look at our formula and plug everything in. So the amount remaining is what we're looking for. So that's X. Initially, we had 2 grams. We're going to multiply by 1/2 to the what power? Well, we didn't tell us the number of half-lives. We have to break it down to the time elapsed, which 44.5 days went by. Oh, no, sorry. Actually, 133.5 days went by. The half-life was 44.5 days. Make sure when you're doing this that the time elapses, the time in the units of time for these two are the same. So you can't have like seconds up top and days on the bottom. So make sure they're actually the same. And when you 2 times 1/2 to the 133/5, this actually, if you do this math, it actually equals 3 half-lives. It's going to give me X equals 0.25 grams of Fe59 left over. Which makes sense. It's less than half because it's more than 1 half-life actually. 3 half-lives went by, so it actually should be a lot less than 2 grams. So a lot of it decomposed and went off into, changed into something else. Let's do something a little bit harder. You might see a problem that's a little bit tougher, and that's this. So let's say we're talking about carbon-14, and carbon-14 is a radioactive isotope of carbon-12. It's naturally occurring in the atmosphere. The atmosphere has plenty of it, and it's always happening. There's a certain ratio of this isotope in the atmosphere, always. So in this atmosphere, it's actually used and very helpful for plants to use for photosynthesis. So plants then take this and use it for photosynthesis. Animals then eat the plants. And so now all of the living objects actually have some ratio of carbon-14 that's equal to whatever's in the atmosphere. So all living objects have this in their system. And it's totally fine. What happens is over time it'll break down. So we have carbon-14. It'll break down because it is radioactive. It'll go through beta decay and it'll change into nitrogen. No big deal. And this takes 5,730 years to occur. Okay, so this isn't actually happening in our lifetime. But what happens when you die, this will start breaking down. So we're not going to be ingesting that carbon-14 anymore, and we're going to start, it's going to start breaking down and decomposing into this nitrogen. So then, if a fossil's C14 ratio is 1/16 that of the atmosphere, how old is the fossil? So we're going to actually say the amount remaining is 1/16 of what the original ratio was. So we're going to say 1/16. The initial amount was 1. Our ratio was the same as that with the atmosphere. Okay, great. Times 1/2. We want to figure out the number, the time elapsed. So we're looking for a little t. And we know the half-life is 5,730 years. Now I'm going to go into logarithms. I'm not going to explain logarithms. If you're interested in learning about logarithms, you might want to check out some math videos, but I'm just going to assume that you know logarithms and say, because I'm looking for the exponent, I'm going to take the natural log of both sides. So I'm going to say the ln of natural log of 1/16 is equal to the natural log of 1/2, because natural log of 1 is 1. Natural log of 1/2 times t to the 5,730. And with natural logs, I can take this exponent and put it in front. So it's now it is not an exponent anymore. So now I'm going to say, okay, the natural log of 1/16 is equal to t, I'm going to say t over 5,730 times the natural log of 2. So I'm going to, 1/2. I'm going to divide by the natural log of 1/2. And so the natural log of 1/16 over the natural log of 1/2. I'm going to bring my calculator out to do that. Where is it? This is 4 equals t over 5,730. So then I'm going to just do basic algebra, multiply 4 times 5,730. And that gives me 22,920 years have passed by. So this is called carbon dating. This is actually a good way to figure out how old a fossil is. And this is a ratio that they use it. It's actually, they use half-lives. So half-lives is a great way to figure out how old something is or how much you're going to have after a certain period of time.